No matter how you slice it, the binomial theorem and the related identities. In the last chapter, we started developing enumerative techniques by finding formulae that covered 6 basic situations. We will continue in that direction in chapter 5. Now, however, we take a break and discuss the binomial and the multinomial theorems, as well as several important identities on binomial coefficients. The proofs of these identities are probably even more significant than the identities themselves. They will consist of showing that both sides of a given equation count the same kind of objects. They just do it in two different ways. Therefore, the two expressions must be equal to each other. This type of argument is the dream of most combinatorists when they prove identities. The binomial theorem. Theorem 4.1 Binomial theorem for all non-negative integers n, x plus y to the n is equals to the summations of n choose k times x to the k times y to the n minus k, where we summing k starting from 0 to n. Proof: consider the product of n sums, x plus y times x plus y and so on times x plus y. When computing this product, we take one summand from each parenthesis, multiply them together, then repeat this in all of 2 to the n possible ways, and sum the results. We get a product equal to x to the k times y to the n minus k each time we take k summands equal to x. There are n choose k element subsets of the set of all n parentheses, so we will get such a term n choose k times, and the proof follows. The binomial theorem has a vast array of applications, starting as early as elementary calculus. In this section, we will see some of its immediate applications to prove identities on binomial coefficients. Theorem 4.2 For all non-negative integers n, the alternating sum of binomial coefficients n choose k is 0. In other words, the summations of minus 1 to the k times n choose k, summing with index I starting from 0 to n, is equals to 0. Proof: applying the binomial theorem with x equals to minus 1 and y equals to 1, we immediately get our claim. Theorem 4.3 For all non-negative integers n and k, n choose k plus n choose k plus 1 is equals to n plus 1 choose k plus 1. Proof: the right-hand side is, by definition, the number of k plus 1 element subsets of n plus 1 braces. Such a subset S either contains n plus 1 or it does not. If it does, then the rest of S is a k-element subset of n braces, and these are enumerated by the first member of the left-hand side. If it does not, then S is a k plus 1 element subset of n braces, and these are enumerated by the second member of the left-hand side. Theorem 4.4 For all non-negative integers n, 2 to the n is equals to the summations of n choose k, summing with k starting from 0 to n. Proof: both sides count the number of all subsets of an n-element set. The left-hand side counts directly, while the right-hand side counts the number of k-element subsets, then sums over k. We can get an even shorter proof applying our fresh knowledge. Proof of Theorem 4.4 Applying the binomial theorem with x equals to y equals to 1. The first proof is an example of a classic way of proving combinatorial identities, by proving that both sides of the identity to be proved count the same object. If we count the same objects in two different ways, we should get the same result, so this is a valid reasoning. Such proofs are ubiquitous and well liked in enumerative combinatorics. This section will contain a handful of them, and many additional examples are listed as exercises. Now let us write down all binomial coefficients in the triangle as shown in figure 4.1. That is, the ith element of row n is n choose I, and the diagram starts with row 0. Then the first few rows of the Pascal triangle becomes the first row 1, the second row 1, 1, the third row 1, 2, 1, the fourth row 1, 3, 3, 1, the fifth row 1, 4, 6, 4, 1, the sixth row 1, 5, 10, 10, 5, 1, the seventh row 1, 6, 15, 20, 15, 6, 1. This diagram is called a Pascal triangle and has many beautiful properties. For example, theorem 4.4 shows that the sum of the nth row is 2 to the n when we call the one element row at the top of the 0th row. Theorem 4.3 shows that each entry of the triangle is the sum of the entries above it. And theorem 4.2 shows that the alternating sum of the rows is always 0. Let us prove one more interesting property of the Pascal triangle. Theorem 4.5. For all non-negative integers k and n, choose k plus 1 choose k plus 2 choose k plus and so on plus n choose k is equals to n plus 1 choose k plus 1. Proof. The right-hand side clearly counts the number of k plus 1 element subsets of n plus 1 braces. The left-hand side counts the same, separated into cases according to the largest entry. That is, there are k choose k subsets of n plus 1 braces that have k plus 1 elements, whose largest element is k plus 1. There are k plus 1 choose k subsets of n plus 1 braces that have k plus 1 elements whose largest element is k plus 2, and so on. In general, there are k plus I choose k subsets of n plus 1 braces that have k plus 1 elements whose largest element is k plus I plus 1 for all I which is less than or equals to n minus k. Indeed, if the largest element of such a subset is k plus I plus 1, then its remaining k elements must form a subset of k plus I braces. This means that if we start with the leftmost element of the kth row of the Pascal triangle and descend diagonally for a while, then the sum of all numbers we touch in this procedure is also an entry of the Pascal triangle. The reader should find out where that entry is located. Finally, let us prove some identities about binomial coefficients that do not directly follow from the binomial theorem, but nevertheless are a lot of fun. Theorem 4.6. For all non-negative integers n, the summations of k times n choose k summing with index k starting from 1 to n is equals to n times 2 to the n minus 1. Before proving the theorem, note that it is not even obvious why the summations of k times n choose k summing with index k starting from 1 to n divided by 2 to the n minus 1 should be an integer. Our proof will show that it is not only an integer, it is equal to n. This hopefully convinces the reader that binomial coefficient identities are beautiful. Proof of Theorem 4.6. Both sides count the number of ways to choose a committee among n people, then to choose a president from the committee. On the left-hand side, we first choose a k-member committee in k n choose k ways, and then we choose its president in k ways. On the right-hand side, we first choose the precedent in n ways. Then we choose a subset of the remaining n minus 1 member set of people for the role of non-precedent committee members in 2 to the n minus 1 ways. We provide another proof that uses the binomial theorem. It also gives us an early hint that sometimes very finite-looking problems, such as choice problems, can be solved by using methods from infinite calculus, such as functions and their derivatives. Proof of Theorem 4.6. Apply the binomial theorem with y equals to 1 to get the identity. X plus 1 to the n is equal to the summations of n choose k times x to the k summing with index k starting from 1 to n. Both sides are differentiable functions of the variable x, so we can take their derivatives with respect to x, and they must be equal. This yields n times x plus 1 to the n minus 1 because of the derivation, which is equal to the summations of k times n choose k times x to the k minus 1, summing with index k starting from 1 to n. Now substitute x equals to 1 to get 4.4. The covered direct combinatorial arguments are so enjoyable that we cannot refrain from discussing one more of them. Theorem 4.7. For all positive integers n, m, and k, n plus m choose k is equal to the summations of n choose I times m choose k minus I, summing with index I starting from 0 to k. Proof. The left-hand side counts all k elements subsets of n plus m braces. The right-hand side counts the same, according to the number of elements chosen from m braces. Indeed, we can first choose I elements from m braces in n choose y ways, then choose the remaining k minus I elements from the set n plus 1, n plus 2, and so on until n plus m in m choose k minus I ways. Considering any one row of the Pascal triangle, we note that the binomial coefficients n choose 0, n choose 1, and so on seem to increase as k increases up to the middle of the row, after which they seem to decrease. As the following theorem shows, this is indeed true for all n. Theorem 4.8. For all non-negative integers k and n, such that k which is less than or equals to n minus 1 divided by 2. The inequality n choose k which is less than or equals to n choose k plus 1 holds. Furthermore, equality holds if and only if n is equals to 2k plus 1. Proof. We provide a computational proof here. We need to show that if the condition holds, then n factorial divided by k factorial times n minus k factorial, which is less than or equals to the result of n factorial divided by k plus 1 factorial times n minus k minus 1 factorial. Let us divide both sides by n factorial, then multiply both sides by k factorial times n minus k minus 1 factorial to get that 1 over n minus k is equals to 1 over k plus 1. Take reciprocals and rearranging, we get 2k plus 1, which is greater than or equals to n, which is equivalent to the condition k, which is less than or equals to n minus 1 divided by 2. So, the theorem is proved. Corollary 4.9. For all positive integers k and n, such that k is greater than or equals to n minus 1 divided by 2, the inequality n choose k is greater than or equals to n choose k plus 1 holds. Furthermore, equality holds if and only if n is equals to 2k plus 1. Proof: this is immediate from theorem 4.8, and the fact that n choose k is equals to n choose n minus k. A sequence of numbers with this property, that is, that it first increases steadily, then it decreases steadily, is called a unimodal. It can often be quite difficult to prove that a given sequence is unimodal. An alternative, non-computational proof of theorem 4.8 is given in exercise 18. A stronger statement is proven in exercise 20.